All right, so this video is going to be on radicals and just introducing them and kind of defining them and how they're formed. So we have seen radicals before, right? We've seen them when we kind of introduced the flow of electrons in a mechanism. So we introduced the single electron arrow, which was the fishhook arrow, versus the two electrons flowing around, which is the normal mechanism arrow that we use. And during that time, we also defined that a radical as a reactive intermediate with a single unpaired electron. So it's just a dot, right? It's not a lone pair, it's just a single electron, okay? And it's formed by homolysis. So remember, homolysis is the splitting of the breaking of a sigma bond and distribution of those electrons equally, right? That's where the prefix homo came from, the same. And so one electron goes to A and one electron goes to B in this case. That's homolysis, as opposed to two of the electrons going to A or B, forming a cation and an anion. Okay, and now let's just go ahead and draw out some kind of defining alkanes, I guess. So we'll draw one with an R group, one with two R groups, and one with three R groups, right? And so if that red dot represents a single unpaired electron, then that would be a primary, secondary, and tertiary radical. Okay, so we are definitely familiar with the idea of primary, secondary, and tertiary, right? And so that's easy enough. But these squared carbons here, the ones that only have that single electron and three chemical bonds, those are electron deficient, right? If you think about it, they do not have an octet. That octet is not fulfilled. It's got 7 electrons around it, right? And so that's why it would be considered electron deficient, okay? And in addition to that, we would classify that carbon as sp2 hybridized, okay? And what does that mean about the geometry? That means that it's trigonal planar, right? And so if it's trigonal planar, that means that the bond angles between all of those is 120 degrees. And if that's the case, we also have, let me draw this out for you. We got a wedge and a dash for our substituents. And then we have a p orbital that's pointed up and down, right? So typically you'll see the p orbital, the orbitals in different phases, right? They're colored red and blue in this case. Those are the same orbital, and that single electron resides in that p orbital, okay? And it's very, very similar to a carbocation, right? Where that carbocation has an empty p orbital, right? The vacant p orbital. In this case, we just have a single p orbital sitting in there, okay? Now, this is going to be important because we do need to know that radicals are trigonal planar because the geometry matters, right? When we're doing stereochemistry and trying to figure out the products, right? So that's it. I think this is very easy for you guys to follow along with if you kind of remember last semester. And so real quick, let me add to this little chart right here. We'll put more or less a methyl radical on the left side. And this methyl radical, as we go from left to right, we have methyl, primary, secondary, and tertiary, right? So we have an increasing stability of the radical, okay? And so we'll talk about stabilities of radicals later, but we do need to mention this kind of trend right here, okay? And the last little fact we also want to throw in there is that there's no rearrangements for radicals, because I did compare it to carbocations, right? Sorry, I kind of just breezed over that, but there's no rearrangements like there are in carbocation reactions. So that's pretty awesome. More details on that to come as well. So the big question, how do you form a radical, right? Well, you can use heat, which is indicated by this triangle, right? The delta symbol. H nu is H, or HV, I probably would call it, is light. And then we can also have a peroxide of some sort. So ROOR is a peroxide with some R group on there. Hydrogen peroxide would just be 2 hydrogens on either side, or a hydrogen on either side. And that's basically how we form radicals, right? So there's obviously much more information that's required to kind of move along with these radical reactions. But before we get into the nitty gritty, let's just talk about the modes of reactivity. So by modes of reactivity, I mean basically what kind of reactions occur. And so we have, let's say, a cycloalkane, just an alkane, right? Some CH bond, and then we have a radical. Those two things can come together. Basically, that X dot grabs an H dot, or a hydrogen atom, and that forms another radical on that cycloalkane, right? And so something with the hydrogen can easily get or undergo a hydrogen abstraction from in the presence of a radical, and that radical now forms a new sigma bond, which is just going to be that HX. Okay, and I've highlighted that in red to show that that came from the radicals. Okay, and then what happened was it formed a new radical with the cyclohexane. Okay, so that's a super common radical reaction that we'll see. And then another mode of reactivity would be a radical reacting with an alkene. Okay, and so the way that looks is you basically split up that pi bond equally, homolytic cleavage, right? And then you form a CX bond as well as a C dot, so a radical on a carbon radical. So there's that CX bond in red, and then the radical there. So if you combine, basically, you might notice that what we're doing is we're typically forming sigma bonds and creating radicals, or we might even neutralize a radical in the end as well. So let's take a look at this one right here. So let's say we have two X dots, so halogen radicals. Those two can come together, bada bing, bada boom. Now, since there's two unpaired electrons coming together, we just form one nice sigma bond that's neutral, and then we don't have anything else forming. So there's no new radical forming. The only time we're going to get a radical forming is when we have a radical reacting with some neutral species that has no unpaired electrons, okay? But there you go. And let's take a look at the last one. So I guess the defining characteristic of these ones is going to be that they are inhibitors. So they prevent radical reactions from occurring, right? And you can also call them scavengers because they will kind of seek out, or scavengers would be another class of inhibitors, but scavengers would seek out radicals, maybe within the body, for example. Vitamin E does a great job of this, and it is called an antioxidant. So that's really what antioxidants do inside of our body. They quench radicals species that are kind of floating around our body ready to wreak havoc, right? You've heard of free radicals kind of being bad for your body. Well, that's why it's important to have antioxidants. Okay, so before I show you this last type of reaction, I want to show you a molecular orbital diagram. Okay, so some of you may or may not have had this in general chemistry. I teach it, but I know not every general chemistry teacher teaches it. But we have, let's say, so this middle set of orbitals, we have sigma bonds and pi bonds, right? And then we also have sigma star and pi star. And on the left side, we have an oxygen atom, and on the right side, we have an oxygen atom. Okay, so when you have atomic orbitals, we are familiar with atomic orbitals, and we know them as s and p orbitals, right? Well, when you make chemical bonds, you have sigma bonds and pi bonds, right? And so when you bring two atomic orbitals together, you make a molecular orbital. And then this molecular orbital diagram is the central one. And that's basically showing how the electrons are organized within an oxygen molecule. So you take the 6 valence electrons from each oxygen atom, and you have 12 in the molecule, and you start adding them to these orbitals, and you add them kind of like you would in the s and p orbitals. So the degenerate orbitals, you put an electron up in each of them, and then you don't start pairing until those degenerate orbitals are filled. And so what that results in is 2 unpaired electrons on this oxygen molecule. And they're unpaired electrons, right? So that's a diradical. There's 2 of them, and they so one of them would obviously be a radical, but 2 of them means it's a diradical, and that's exactly how oxygen reacts. So you know that things in the presence of oxygen will kind of break down, right? Like if you leave olive oil out, for example, it'll spoil. over time. And you can draw this Lewis structure to kind of visualize how that might react, or how that might kind of look, right? So Lewis, obviously the oxygens don't have the octet fulfilled, but this shows how they react. And it also shows how it is paramagnetic and can actually interact with magnets. And so the molecular orbital diagram is it's great for kind of explaining a lot of the anomalies we see with oxygen. And this diradical species can react in the same manner as a single radical species, where you have the single electron reacting with an X dot to form that OX sigma bond. Okay, and so this would be kind of one of the examples of an inhibitor. So if you do a radical reaction in the presence of oxygen, then it's going to react with a radical species, so that X dot can't do any kind of chemistry, right? So if we wanted that to abstract a hydrogen to allow the chemistry to go further, oxygen's going to ruin that for you, okay? So the presence of oxygen prevents or slows reactions down. This is like amazing tool to identify if a reaction is in fact a radical mechanism, because sometimes we don't know. And so the presence of oxygen slowing a reaction down or preventing it from happening at all can actually help you identify a mechanism as a radical mechanism. And antioxidants like vitamin E are similar. And so they will quench radicals. So if we actually put this diradical oxygen in the presence of vitamin E, or maybe oils, like I said, olive oil will spoil. So oxygen, again, the diradical, will react with the pi bonds in the fats of oil, and you form this new radical species right here. And so the reaction definitely proceeds further, and we can go over that later, but I just want to show you another way for this. This is essentially a fatty acid. It's the moiety of a fatty acid, so like a functional group within that, and it quenches the radical species and doesn't allow them to wreak havoc anywhere else. And so that's kind of just a quick introduction to radical species. I hope we at least drew your attention here. And by we, I mean me. I don't know why I said we. You know how I do. I'm silly, y'all. I'll see you soon. Let me know if you have any questions on this, but move on to the next video first.